Hello, welcome. In this short video, let us look at the area under the beta distribution. A beta distribution is defined as beta of mu given the parameters a comma b is equal to the gamma function a plus b divided by gamma of a multiplied by gamma of b, then mu power a minus 1 minus mu power b minus 1. So this is the beta distribution. And our goal is to prove that the area under the beta distribution, that is integral 0 to 1 beta of mu given a comma b is equal to d mu, of course, equal to 1. So that is our goal. Now let us start with the definition of a gamma function, which is defined as gamma of a is equal to integral 0 to infinity e power minus x power a minus 1 dx. So gamma of a is defined as this integral. Now let us start with this product, gamma of a multiplied by gamma of b, which is going to be equal to the product of two integrals, that is 0 to infinity e power minus x power a minus 1 dx, integral 0 to infinity e power minus y power b minus 1 dy, which is again equal to integral 0 to infinity, keeping the x terms, x power a minus 1 here, and then we have integral 0 to infinity e power x plus y, e power minus x plus y multiplied by y power b minus 1 dy, of course dx. Now let x plus y equal to t, that means y equal to t minus x, dy equal to dt, and the limits of t are 0. When y is equal to 0, t tends to x, and when y equal to infinity and y tends to infinity, t tends to infinity. So these are the limits of t. So rewriting the integral, we have 0 to infinity x power a minus 1 integral x to infinity e power minus t minus x power b minus 1 dt dx. Now let us look at how do we change the variables. From the integration, we can clearly see that the integration limits are as follows. That is, consider two axes. This is for x-axis and this is the t-axis. Clearly, the integration area is between t equal to x to infinity. That is between this line t equal to x to infinity. That is this. And x limits are from 0 to infinity. So the integration area is under this, between these two lines, basically between the lines t equal to x to x equal to 0. Now by changing the variables, that is reversing the variables, we can see this integration as between x equal to 0, that is from this line to this line, that is x equal to t, and t from 0 to infinity. So thus the integral becomes 0 to infinity e power minus t integral x equal to 0 to t, that is the limits of x are 0 to t, and then we have x power a minus 1 t minus x power b minus 1 dx and dt. So thus this integral is rearranged, or by using change of variables is written as this integral. Now let x equal to t mu, where t is fixed, then dx equal to t times dx d mu, and the limits of x were 0 to t, right? And then the limits of mu becomes 0 to 1. So the integral becomes 0 to infinity e power minus t integral 0 to 1 t mu power a minus 1 t minus t mu power b minus 1 t d mu dt. Now again rearranging this integral, we have integral 0 to infinity e power minus t power a minus 1 t power b minus 1 t dt, integral 0 to infinity mu power a minus 1 minus mu power b minus 1 d mu. And this integral is written as 0 to infinity e power minus t t power a plus b minus 1 dt. And this is again 0 to 1 mu power a minus 1 minus mu power b minus 1 d mu is equal to, and this is the definition of gamma function of with the parameter a plus b, and this is nothing but the variable part of the beta distribution, that is integral 0 to 1 mu power a minus 1 minus mu power b minus 1 d mu. And since we the left hand side, the original left hand side is equal to gamma of a times gamma of b, and if you take this product onto the left side, we have the beta distribution, that is gamma of a plus b divided by gamma of a multiplied by gamma of b, integral 0 to 1 mu power a minus 1 minus mu power b minus 1 d mu is equal to 1. Therefore, integral 0 to 1 beta distribution of mu given the parameters a comma b d mu is equal to 1. Hence, the beta distribution is normalized. Thanks for watching.